Welcome to another edition of Sparky Help, as this is the easy guide to cable sizing. So what is it we need to do? That way we can break it down into steps. It's relatively straightforward. First thing we need to do is calculate the design current, which the regulations call IB. So that's the actual current that's going to flow in the circuit, drawn by the load itself. Obviously, if the manufacturer provides you with that information, you can just get it out of the instruction manual. If not, you need to calculate it. So it's a simple, straightforward calculation, or calculations if you need to require to work out what IB happens to be. So we have got power divided by volts, which is obviously very straightforward. Power divided by the cosine and voltage multiplied together. So if you've got the power factor, and the last one on there, if you have a three-phase circuit, then it's power divided by the square root of 3 multiplied by VL, so that's the line to line voltage, times by the power factor, whatever that happens to be, if you have one. So once you have IB, the next step you need to do is carry out IN. IN is the protective device size, and IN has to be equal to or greater than IB. It doesn't need to be the next size up or keep going. It doesn't need to be just in case. It just needs to be equal to or greater. The only time this exception kicks in is that bit of paper again, the manufacturer's instructions. If the manufacturer says put a particular type of fuse in, then that is what you should be putting in. But otherwise it can be equal to or larger than. But please do refer back to manufacturers for any specific items of equipment. Once you have that, then the next thing you need to do is find out what IT is. IT is something that is in the BS7671 and along in the on-site guide. And it is calculating the tabulated rating of the cable required. Now, obviously, it does depend where you run that cable and how you run it and what type of cable. All these factors come into play. Ultimately, though, the whole thing with cable sizing is about heat of the cable. We don't want the cable to get too hot or go beyond its temperature range. So that's what we need to do. The formula for that you can get from BS7671, which is in Appendix 4, or it's in the on-site guide, and it is equal to or greater than or equal to IT is what we're looking for, and it's based on the fuse size, and the fuse size divided by the correction factors. Now I've named a few here: CA, CI, CG and CF. So we'll look at each of those, but you apply the ones that are relevant for your installation of your circuit. So once we have that, there's your IN. CA, so what is that? That's for ambient temperature. So that's an ambient temperature different to what the cable is rated at, and what you'll find is in BS7671 and most manufacturers, they quote their cables and test their cables in an ambient temperature of 30 degrees. So if you put your cable in any temperature that is different to 30 degrees, then what you should be doing is correcting for that temperature. Ideally, if it was in a colder environment, that will work to your advantage because it will cool the cable, and in theory you could apply a factor that would downsize your cable. But if you do put it in an environment that is hotter, then you can apply a factor to compensate for that. So that's CA. CA for ambient temperature. Another one, not necessarily in the order of the formula I've got up there, but certainly the order I've written it down, CG, cable grouping. Again, this is all heat related, about cables being grouped together, because collectively each cable is going to run up to a maximum temperature of 70 degrees. So therefore, if you lay that cable or install that cable with other cables that are running at 70 degrees, then they're all going to get warm, and they're going to get warmed up by the surrounding cables, and therefore will not be able to dissipate that heat. So the more you group a cable, the worse it is for those cables in that particular enclosure. So a grouping factor will compensate for that and ultimately make all your cables bigger. CF. Rewirable fuse. This is a BS3036, so this is an old Wilex style protective device which is still out there. People often refer to them as being a bit crap, to be quite honest. However, they do still work. People often think they take longer to blow. That's not the case. They still have to disconnect in exactly the same time as all the others. The one factor that comes into play, which is why it has its own correction factor, is that a rewirable fuse takes more current to make it blow. So that means the cable itself has to be able to withstand that extra current to blow the fuse in the time required, which, as you've probably looked at other videos that I've done, is either 0.4 or 5 seconds. Obviously there is a 0.2 and there is a 1 second also for protected device disconnection size at times. CI is thermal insulation, so that's very difficult to avoid nowadays with cables installed in modern premises, but if cables are installed in thermal insulation, then the whole point of thermal insulation obviously is to keep heating, which is not good for our cables, so therefore we can apply a factor to minimise that effect. If you were to look at the regulations, what does it basically say in there? Well, effectively what it says is please try and avoid installing cables in thermal insulation. So if you can, avoid it. If you can't, then we can apply a factor to your calculation to compensate for that. I've stuck another one in there because there are others. This is CD, so depth of cables buried in the ground. So there is tables on that, and there are correction factors for cables buried in the ground. And what you'll find is when you look into it, it talks about whether the cable is in a duct or not in a duct and how deep it is. There's lots of different factors that apply. So CA is the first one we looked at. So from Appendix 4, this is where this comes from, Appendix 4 of BS7671, this is just an extract from it. As you can see on there, Table 4B1, and it says CA for ambient air temperatures other than 30 degrees. As mentioned earlier, that is because the manufacturers test all their cables in an air temperature of 30. So you will see that the correction factor, if you can see that along there, for all 30 degrees, the CA is 1. And if you multiply or divide a number by 1, nothing happens. So you can ignore it. But obviously, if you have an air temperature that is lower than 30 degrees, then the correction factor goes above 1. And if you divide a number by 1, what it will do is make IT smaller. So you're basically looking at, on these particular tables, you're looking at your temperature on the left-hand side, and then it's the type of insulation, because the bit that limits current through all cables is not the conductor, it's actually the insulation. The insulation will fail long before the conductor itself does. So that's basically the bit we're interested in. So what is the actual cable insulated material that I've got around it? So there's the CA, which if you went to the BS7671, you will find this, and you'll find a bit more information than I've shown on here. Thermal insulation. This is not in Appendix 4, this is in Part 5 of BS7671, and it comes from Table 52.2, and it says cable surrounded by thermal insulation. So this is the amount of cable, so if it passes through some insulation, and it's the amount of cable in insulation. As you can see, it doesn't take much to go through it, so you've got there 50mm, 100mm, 200mm, 400mm. Bizarrely it stops there, I don't know why it does that, but actually if it goes through half a metre or more, then the derating factor is 0.5. So in other words, if you go through anything above half a metre of your cable goes through insulation, it derates your cable by half. Hence what they say in the BS7671 is avoid it at all costs. But these are the correction factors if you put your cables through thermal insulation. If you avoid it, then you don't need to worry about it. CG, another very common one within BS7671, because obviously most cables at some point end up being grouped somewhere or other, and this is the table that it comes from, or one of the tables that is in there for grouping, but it's probably the most common one, this one. Table 4C1 doesn't say grouping, doesn't say CG on the table, so personally I would write next to it so you know that's what it refers to. But as it says on there, there are other tables as well that may well apply, but you'd need to look in BS7671 and read the descriptions. I've only shown a selection in here. So you've got the second column down, you've got the description of your installation. So it says bunched in air on a surface embedded or enclosed. So that would be in conduit or trunking or something like that. Single layer on a wall, well, that's exactly what it says on the tin. It is single layer on a wall. And I've stopped at that point there to show you. And then across here, you've got a number of circuits. And remember, that is circuits, not conductors. So don't get confused when you're putting in a circuit and it's got 3 conductors with it, you don't start counting each conductor, it's number of circuits that you're installing. The only thing to remember when doing any of this, especially in exam questions or anything else you're doing, is you must include your cable that you're adding to it. So if the question says it's going to be added with 2 existing circuits, then that 2 existing circuits will include your one, so therefore there are 3, and you'd basically look down the column here and then read off whichever description you're going for to put in your correction factor. They've conveniently put across here which method it also applies to, so if you know the method then you can just look straight to the right hand side if that works for you. CF, as spoke about, this is the dreaded rewirable fuse. So when these blow, you're looking for that little bit of cardboard on top of the distribution board with the bit of wire still wrapped around it if it still exists. If not, you've got a disc board change. So where does this one come from? Well, it's all written in the words. It's in many places in the book, to be quite honest, is what it refers to. But this is the paragraph within the BS7671 in Appendix 4 that's tucked away, and it's about the rewirable. And it's this part in the middle here that you're interested in. So it's the 0.725 is the factor. The 1.45 divided by 2, that's how they arrive at it. What they are the fusing factors. So as far as the regs are concerned, all protective devices except for the rewirable fuse have a fusing factor of 1.45, my apologies. And a rewirable fuse has a fusing factor of 2. So what does that basically mean? If you have a 10 amp protective device that's not a rewirable, then in theory it takes 14.5 amps to make it blow. If it's a rewirable, then it's twice the amount, so in theory it takes 20. So you can understand, therefore, if it takes 20, it takes more current. The cable, therefore, may have to be bigger and is made bigger to compensate for that extra current for the duration of overload or fault that you may well have. So 0.725 is the factor if you put a rewirable fuse on. Obviously, if you don't, ignore it. Then what do you do? Well, once you've gone through those calculations, you've decided what you're going to put in, then you select the cable from BS7671 that carries the amount of current that you've calculated. And what you're trying to find is you're comparing against the IZ values. Now, IZ is the actual rating of the cable, okay, that you're looking to install. So in the regulations, it doesn't quite say like this. It says it in word form, but what you're basically doing, we have just worked from right to left. So IB is what you start with. You then select the fuse based on IB, which has to be equal to or bigger. IT is what we calculate if you need to calculate it, and that has to be greater than or equal to IN, the fuse size. And then finally, the cable rating itself has to be equal to or bigger than IT is your final selection point. So that's in the regulations, and that comes from chapter 43 in BS7671, where it refers to all of this regards to cable calculations. Ultimately then, we do select the cable against whichever type of cable we're looking for. So in this case, what I've got here is, again, from Appendix 4, and as it says on there, a single core, 70 degrees C, thermoplastic, insulated, non-armoured, with or without a sheath. So this is single core, so this could be your tails to your meters, okay, which has a sheath on it. People might refer to it as double insulated, but the regs refer to it as with a sheath. Or this is going in conduit or trunking, so it's just singles with one layer of electrical insulation around it. So again, what have we got down here? So in your first column, you have conductor sizes. Again, I've only stopped at 2.5, but this would go up to 1,000 mil in conductor size. And then across here, you've got your installation methods that you may or may not select from. So you need to choose which one. So if we'll go and clip direct, you'll see it then subdivides into 2 further columns, and here you have single phase in column 6, and in the right hand side you have 3-phase circuits in column 7. So you just need to make sure you're reading from the right one. Up the top here it says the ambient temperature to which all the manufacturers have quoted these at. So these are the current carrying capacity IZs of the cable at their specific way they're installed. So that one there is for 30 degrees, and what will happen is it will run at 70. So this is the conductor will run at 70. So if we look at this, if we go to the 1.5, if it's clipped direct, it can carry 20 amps at 30 degrees C. The conductor, when installed in that way, the conductor will get to 70 degrees C. finally, once you have all that, the very last step is actually check the volt drop for the particular circuit. Now that has to be under 3% or 5%, depending whether it's a lighting circuit or it's another type of circuit, respectively. So 3% or 5% of the nominal voltage to which you started with. So how do we do that? Well, it's the volt drop equals the millivolt rating times IB times the length of the cable. Where do we get this information from? Well, we get it from table, if we're following on from the previous one, which would be over the page on BS7671, so it's 4D1B. And here you can see then, this is the same cables that we were just looking at a minute ago. So here's our 1.5 mil squared. And if you were working with DC, that would have been a millivolt. As it happens, they're almost all the same. But if it was single phase, which is the bit we're in, over here it would be 3-phase. So I've cut that bit off. So here's the single phase, and if it was enclosed in conduit and trunking, it would be 29 millivolts per amp per meter. What I say to all students is, see that / there? That becomes a multiplier, because that's effectively your formula. So, as always with all these things, the best thing you can always do is have a go. So let's just work through an example with you. So calculate the size of the cable for the following. So we need information in order to work this out. Obviously, if it's your job you're working on, you would know, you'd check, make sure you're correct in what you're doing. So we need to know the load. So here's the load, 8.4 kilowatts. We need to know the length. Okay, so we're going to say it's 28 meters in length. We need to know the type of cable we're going to use. So we're going to do cable. It's going to be a single core cable, thermoplastic, 70 degrees C, ambient temperature 35 degrees C, in trunking with 2 other circuits is how we're going to install it. The protective device we're going to put on is a BSE N60898 type B, so that's a circuit breaker. So we need to size the circuit and everything to do with this particular circuit here. So first things we need to do, calculate IB. So therefore straightforward, power divided by volts. So that's 8,400 divided by 230, we get 36.52 amps. So that there is our IB. Remember, the next thing we need to do is select our protective device. And again, this comes from chapter 41 of BS7671. You could also go to appendix 3, or unless you happen to know what the protective device sizes you want without looking them up, then obviously do that. So on here we need a protective device that is 36.52 amps or more. And as you can see on here then, what we would go for would be the 40 amp. Okay, so that's what we've got. IN is greater than or equal to IB, therefore IN from our previous table would be 40 amps. Well, what's next? Next, we need to calculate IT. So here's what the formula would be. It's IT is greater than or equal to IN divided by CA and CG, because in the question it talked about the temperature and it had grouping applied to it. So you only apply what is relevant, not everything. Okay, so that becomes 40 divided by 0.94 times 0.7, and that comes out as 60.79 amps. So the IT, so what the tabulated rating of the cable needs to carry, is not the 36 amps that you started with, not even 40 amps, but because of how it's been installed, it needs to carry 60.79 amps. So where does the 0.94 and 0.7 come from? It comes from these locations here. So these are CA, and for the CA it was 35 degrees, it was a thermoplastic, so that's where our 0.94 comes from. So that one's straightforward enough. Once you know where the tables are, you can get all this information. The other one is CG, so remember it said with 2 other circuits, so that's 3 circuits in total. So here's our 3 circuits, bunched in air, that's our trunking. So 0.7 is where we need to go. Okay, so that's where our correction factors come in, and once you apply that, you get 60.79. What we're now able to do, hopefully, is select the cable. So we go to the type of cable we've selected, which is single core thermoplastic. We go for method B, enclosed in conduit or trunking, and we go for single phase, and we go down this column here until we get to a value that is 60.79 amps or more. So it takes us right down to this one here. So we take the 76 is what is the next one, and therefore we read off to the left, and that becomes a 16 mil. So the IZ of that cable is actually 76 amps, but 16 mil is what we actually require. So that's our cable size, but remember the last thing we need to check is volt drop. Volt drop is based on millivolts times IB times the length. Remember the millivolt we need to find. So that would be the next page over, and we know our method, it's single phase, method A or B because it's enclosed in trunking, and look at 16 mil, and it's 2.8 millivolts is what we're looking for that particular circuit. So when we put that in, it's 2.8 times 10 to the minus 3, okay, because it's 1,000th, times 36.52, which is design current, times 28, which was the length, and that gives you a grand total of 2.86. For this particular circuit, the maximum you would be allowed would be 11.5 volts drop. So that is well under, and because that is well under, it means that the 16 mil cable that we've selected is okay. So that's cable sizing very briefly and very simply. It doesn't take too long to do. Obviously there are apps out there that do work. You are trusting the apps, but if you wanted to check quick calculation for yourself, if you're doing an exam, then this is very simple and very easy to get quick marks on. Thank you very much. Please subscribe, please have a look at other videos, and thank you very much.